Okay, so what we're going to look at today is the evolution beyond Lewis structures into what we call valence bond theory and then molecular orbital theory. And for what we go or need moving on, the most important one is Lewis theory. That's why we're going to spend, next week Tuesday in lab going over some more Lewis structures, and we'll spend almost all of our time on that. These two theories, they'll show up on the test. There'll be questions on them, but they're kind of dead ends a little bit in chemistry in that we're not going to go or need as much depth anymore in these to kind of be able to answer the question. So one of the things that's tough about this section is it's very picture heavy. So I printed off a bunch of the pictures for you, and most of these are from your book, I think, actually, because one of the reasons I liked your book is because your book has excellent pictures. And some of them might be from other books, and in which case we'll do them. So what we'll do is we'll kind of go back and forth and hop back and forth between the pictures and having some blank slides in which to talk about stuff. So the other thing I also recommend is read the book. This lecture works much better if you sort of read a little bit, look at the pictures, think about it, go back, read a little bit, look at the pictures, think about it. Meaning this sort of material, I think, is much more suited to reading where you have some time to think and ponder and look at the pictures than a lecture format where, I'm saying something, I point it out in the picture, and then we go on without maybe that, 5 minutes to stop and think about it, or the few minutes to kind of think about that idea. So sometimes I really think reading a book is actually better than a lecture for certain types of material. And then for certain things, I think lectures and having that possibility of give and take if you have a question or slowing down or something is also kind of useful. So what we want to look at is that basically there's two big flaws in Lewis structure, or in the Lewis theory. The first one is that it fails to predict bond lengths and bond strengths. Bond length and strength. So for instance, if I take a look at the Lewis structure diagram for, just like say HCl versus say, CO2. It says nothing about how long or how big this bond is. And the biggest failing with it, and I'm not even sure I would say it's a flaw in Lewis theory. Lewis theory was never designed to answer these questions. Lewis theory was designed or came about mostly as an observation that things like to have octets and that we can predict electron or the shapes of molecules very well from Lewis theory. So I should maybe point out, maybe we'll go, well, we won't go back a slide because I have stuff there, but we'll at least point it out here is that, Lewis theory wins for some things. And maybe this is something I don't stress often, but Lewis theory wins because it's easy, meaning octets are pretty reasonable. It wins because it predicts shapes based on valence shell electron pair repulsion theory. And so, Lewis gets a lot of stuff right, and it gets so much stuff right that we actually use it for the rest of the book as our main fallback when we want to talk about the shape of molecules and stuff. And like I said, it gets things wrong when we get into the nitty-gritty details. And so maybe calling it a flaw in Lewis theory or Lewis structures isn't a very good way to do it because, it's a non-mathematical model. Unless you think counting to 8 is hard math. And then Lewis structures are a very mathematically oriented model, right? Because you got to count to 8 an awful lot. The other thing it fails as is it fails to explain magnetic structure, the electronic structure. Of atoms. Meaning it gets the concept of if things are paramagnetic or diamagnetic wrong. And we'll talk more about this because valence bond theory tends to get this wrong too. So we're going to put that off till MO theory, the molecular orbital theory, to explain the details behind it, because it's pointless to say it now, then come back and repeat it in 30 minutes or something like that. And so Lewis structure kind of, I guess maybe we'll even throw a third flaw in there, is if you take a look at it, for instance, carbon has the electron configuration 1s2, 2s2, 2p2. And somehow, you know, it wants 4 bonds, or, you know, it wants to find 4 electrons to share, but those 4 electrons go in p orbitals that look like this. If I kind of drew this out this way, carbon looks like this, right? So for instance, it's got this empty p orbital. And if it fills it, it's not going to be sharing those electrons. Those electrons kind of belong to it, meaning it would have to somehow try to get 2 shared electrons in 1 p orbital. And so the way that the orbitals work like that, and the way that Lewis structures predict that, you know, an s orbital and p orbital make the same bond, is difficult and doesn't really work. And so instead we have what is called valence bond theory. Valence bond theory. And sort of the big tenets of valence bond theory is simply that the sharing of electrons is between the overlap of those atomic orbitals. So bonds are shared electrons in overlapping atomic orbitals. And it becomes mathematical in that it says that the amount of overlap is proportional to the bond length, and it's proportional to the bond strength. Meaning, the more overlap I have, the stronger that bond's going to be. And since we can do mathematical calculations to calculate the shapes of these orbitals, to calculate the amount of overlap from quantum mechanics, we could potentially, with this theory, calculate the bond length or the bond strength mathematically. Now, the math is way beyond this, and we're never actually going to calculate a bond length or a bond strength. Instead, what we're going to use this theory to do is it's kind of a stepping stone between Lewis structures and molecular orbital theory. And it does start to explain things and give us some ideas about how kind of more complicated this really gets than simply counting to 8 on your fingers. So some other tenets is basically that the overlap or the sharing has to be between opposite spins. So what that's saying is that, for instance, if I have a couple s orbitals here and I'm showing them overlapped, that the electron in one s orbital and the other s orbital have to be in opposite spins to be in that overlap. So you would have one spin up, one spin down. That really is just an extension, if you remember, of the Pauli exclusion principle. Actually, no, I'm sorry, that's one's Hund's rules. And so each atom keeps its normal orbitals. And we've already got the amount of overlap is proportional to the bond length and bond strength. So for this process to work, we have to kind of take a look at what things are happening. So for instance, if I take a look at hydrogen, what valence bond theory is saying is that I've got two 1s orbitals that are overlapped like this, and there's my 2 electrons that are shared and my 2 hydrogens. If I have, for instance, a hydrogen and a fluorine, because fluorine has 1s2, 2s2, 2p5, that means that electron or that orbital that's shared is a p orbital, and so you get something like this, and then the other one is the overlap with p orbitals. So again, here's my overlap. Or, you know, for instance, if I have 2 fluorines, the overlap has to be between s or p orbitals. So you can get different types of overlap depending upon what orbitals are filled in an atom and what orbitals are left empty. Now, we run into a small problem here, though. And this is where valence bond theory gets a little bit more complicated and where we have to resort to looking at quantum mechanics to kind of explain some things into, as knowing that, for instance, if I plug the numbers into the mathematical model, that this is how it works out, whereas we're incapable of doing that in class. So you have to take a little bit of what I'm saying on faith. If I take a look at a complex molecule, now you may not think it's that complex, but if I take a look at methane, valence bond theory runs into a problem in that if I take a look at it, carbon, first off, has 1s2, 2s2, 2p2. And so what its empty orbitals look like, so here's my 1s, 2s, and those are my 2p orbitals, is something like this. So it's only got, it has different sorts of orbitals. And so somehow it can't share electrons in an empty orbital. Meaning, if I take a look at it and I draw the hydrogen in red, so we'll switch colors, so my hydrogen electrons are in red. Well, I could share one electron with hydrogen. I could share another electron with hydrogen, but I can't put two electrons in hydrogen here, meaning that this can't share electrons if the orbital is empty. And so what that really means is that valence bond theory starts to break down until we have to add two additions. And the first addition that we're going to add to it is the concept of promotion. The idea is that we take an electron in a lower energy level, but it's still in the same shell, meaning we can't violate it too much, and place it in a higher energy level orbital. Place it in a higher energy orbital. So what we're really saying is that if I take a look at just the outer electron shells for carbon, so this is carbon, I have something like this. What it's going to do is it's going to promote one electron to that empty orbital. So we promote a 2s electron to a 2p orbital. You guys with me so far or not? And so what happens is we get a picture that looks like this. We get our 2s orbital, and we have our 2p orbitals, and so now I've got 4 electrons that I can share, right? So it's easier to share 4 electrons now. We have a special term for these. We call the normal state of an atom its ground state. And this is our excited state. And to go from the ground state to the excited state, I have to add energy. Meaning it takes energy to take an electron and move it a little further away from the nucleus, right? Because remember, this picture is looking like this. And so what I'm saying is, here's my 2s orbital. Here's my 2p orbital. I'm going to take an electron from the 2s, and I'm going to promote it to the 2p. So I'm moving it a little further away from the nucleus. So it takes a small amount of energy to accomplish this. So this works okay, because now, for instance, I guess I have to switch colors, but if I say the hydrogen electrons are blue, then, I can form 4 bonds with that. And so what that gives me as a picture, though, is something weird, because notice that I've got a 2s overlap, but I've also got 2p overlaps. And so if I try to think about drawing that in terms of a picture, here's my carbon atom, and here's an s orbital. And what we're saying is that one of the overlaps is with a hydrogen over here, so there's carbon, here's hydrogen. And then carbon's also got these p orbitals, and those can also overlap with a hydrogen. And so, here's my overlap from that. So what this is saying is I've got 3 bonds between p and s orbitals, and the p ones are on carbon, and the s orbitals are, of course, the hydrogen. And I've got 1 bond between an s and an s on carbon and hydrogen. Therefore, it predicts that 1 bond is shorter and stronger because of more overlap. The trouble is that in real life, or basically experiments, all 4 bonds are the same. So I got to be honest, if our theory can't even explain methane, which is about as simple as a molecule as it gets, CH4 is not terribly complex, is it? I mean, considering we can have molecules with thousands of atoms in them and try to explain that. So if our theory, valence bond theory, can't get that part correct, it's not going anywhere very fast. And so we have to do one more little fix or kind of band-aid or add one more tenet to it. And it's something that we've already seen a little bit before. Do you remember when we drew Lewis structures? We were talking about how you can draw more than one Lewis structure for something, and we talked about those resonance structures, kind of, that it's the overlap of a bunch of different things, and that there's more than one correct answer. So the same thing kind of happens here, except we call this hybridization. Now when you think of hybridization, what do you think of? Yeah, you think of a cross between usually like plants or animals, right? Well, that same thing is what we're talking about for the electrons. We're going to actually mix the wave functions, which is exactly like I like to think about it as we're breeding them to make new wave functions. Or what we're saying is that if I have carbon like this, so that's my 2p and my 2s. So this is carbon, and it's in its excited state. Then what we're going to do is we're going to hybridize these orbitals. Or a lot of times I think about it as we mix orbitals. Or you can also think about it as, if we take colors, we can mix colors together and get new colors, right? It's all kind of the same idea. And so what we're going to do is we're going to breed them together. And it turns out that when we mix them right, we get what's called sp3, or basically we get 4 identical orbitals. Which is good because that would lead to 4 identical bonds, which means that it agrees with the experiment. And frankly, one of the things that's, easy or tough, take your pick, about coming up with theories to explain things is you've always got lots of experiments that people have done to compare to. And so if your theory can explain a bunch of experiments, then people start to go, hey, we like this theory. And then when your theory can't explain some things, people are like, well, that theory needs some work. So, valence bond theory, by making these small alterations to it, it begins to explain more and more the experiments we see. Because Lewis structure, of course, can't explain any of this. And other than the fact that we know carbon makes 4 bonds with hydrogen because it completes octets. So it predicts the model, or it predicts that it exists, but it doesn't predict much beyond that. Now, what I mean by hybridization, and this is where we're going to draw, I'll go and say you can go ahead and look on the pictures in your handout. Whoops, I forgot to give myself a picture of the handout. So if you look on the first page of that handout that I gave you, that should be showing the mixing of the orbitals between to form the sp3 hybrid orbitals. So what we're saying is that we literally are taking an s orbital plus 3 p orbitals. Okay, so now normally when we're breeding humans, it's one guy, one girl, right? When we're breeding orbitals, it gets a little kinky in here in that it's kind of like having some group sex or something like that. I don't know if I should even say that on tape. But we're going to breed those 4 orbitals. So we breed them. What we mean is that we're hybridizing them. And what it really means is that we're mathematically combining their functions together, combining the wave equations. And this is where I say that, you know, honestly, we're not going to do it in class. Even when I got to it in grad school, I think we showed sp3 mixing, meaning we took the computer equations and we gave them to a computer and said, okay, mix it together, and looked at the result. And then he said, yeah, everything after that's even twice as hard. And I was like, wow, man, chemistry gets really freaking hard if, you know, we can barely mix orbitals in grad school. We're, you know, man, there's some smart people out there. That's all I got to say. There are some mathematical geniuses. So what we get from this is we get 4 orbitals that look like lopsided orbs. So they have a large lobe and sort of a smaller lobe. And that when we combine those all 4 together, okay, here's Jay's wonderful drawing skills. I'm not even sure I should attempt this. I should simply show you the picture in the book. What you end up getting is you get, you know, a little lobe and a big lobe, and a little lobe and a big ass lobe, and a little lobe and another big ass lobe, and a little lobe and a big ass lobe. And it turns out that this predicts a tetrahedral shape for where those orbs are, which is pretty good because that's also what Lewis predicts for the shape of this molecule. So to me, this is where it just gets like, I don't know if I want to say mind-boggling, because maybe if I was really brilliant mathematically, I'd be like, oh, duh, of course it works like that. But so we're taking a globe and a bunch of dumbbells and mathematically doing something complicated to them above my head, and it spits out the exact result that we expect from Lewis structure. It kind of reminds me a little bit of that aha moment when you're looking at, you know, all these sp, d, and f orbitals and recognize that quantum mechanics predicts the shape of the periodic table perfectly. And then when you realize that mixing orbitals together predicts the shape of molecules perfectly, you know, to me, it becomes more and more real. I'm like, okay, so I mean, I can understand the shapes, I can build the models, but when complex mathematical equations spit out something that simple, that elegant, I usually am like, wow, that's amazing. Same thing with quantum mechanics. 4 quantum numbers and a bunch of ugly equations spit out the shape of the periodic table. Simply amazing to me. Maybe it's not so amazing to you guys. I don't know. Maybe you guys are like 10 times smarter than me. I don't know. Good, you know, tough call on that. Certainly there are people that are much smarter than me in life for doing these. So we call these sp3 hybridization simply because we took one s orbital and we took 3 p orbitals and we mated them together. That kind of makes sense, doesn't it? And I guess I should, since we got the pictures here, I can go ahead and, you know, show you that concept of the good, lovely pictures. And I don't know, you can tell me. I actually think my picture for that isn't so bad. It's the rest of them that are hard to draw. This is not too hard. There we go. So, you know, like I was saying, here's my s orbital. Here's, you know, 1, 2, 3 p orbitals. I hybridize them. I get that tetrahedral shape on the right, and each individual orbital has that characteristic where it's got one large lobe and one small lobe. That gives that idea of what it's called directional bonding, where it literally predicts that tetrahedral shape, which is, to me, simply amazing. So, how many shapes did we have when we went through Lewis structures? We had trigonal planar, well, okay, we had linear, right? We had like trigonal planar, tetrahedral. The one with 5 was trigonal bipyramidal, and the last one was octahedral, right? So, to me, if this theory also predicts all 5 of those shapes, first off, it matches up very well with Lewis theory on shape, which is good because Lewis theory gets shapes right. And now it's going to allow us to figure out all that overlap of orbitals and things like that in order to figure out the bond lengths and bond strengths, if we actually went through the nitty-gritty part of it. We're not going to go through all of it, though. So if we take a look at the next set of hybridizations, oh, so that's showing, I guess this is a good picture too. So here's my hybridized carbon atom. It's got 4 lobes now that are the same. And then it can pair up with the 4 hydrogen atomic orbitals, and notice that the overlap is now the same. Therefore, the bond is the same. So, valence bond theory is complex in that, I mean, what it predicts is not terribly complex, but in order to mathematically go through and mix all these orbitals and stuff together, like I said, we didn't even bother doing that in grad school. It was such a pain in the butt. So, why would we do it in this class? I don't know. So, let's take a look at the next set of hybridizations. This one is sp2. So notice that I'm taking one s orbital, I'm taking 2 p orbitals, and I'm mixing them together. And then I get this shape right here, which simply predicts trigonal planar. Notice that all 3 of those lobes are in their exact same plane, right? And notice that it still predicts that odd-shaped lobe where it's got a large lobe and a small lobe. And then the other nice thing that it predicts is, notice that the blue ones are the hybridized orbitals, and there's 3 of them. And then it's got 1 leftover p orbital, which turns out to be very important. In fact, maybe I should get my molecular models out real quick here. For those of you at home, you'll have to either build one or kind of play with it. But one of the things that we decided when you were building your molecular models, for instance, is if I had something that was trigonal planar, notice that we said that it had 2 single bonds and then there was a double bond on it, right? And that was an example of something that's trigonal planar, right? So what this is going to also allow us to do now is to talk about how that double bond is formed. So for instance, if we take a look at the molecule that looks like this is probably the easiest example. This has that trigonal planar shape, trigonal planar. And so somehow we need to explain the carbon-carbon double bond. And I don't know, a certain part of me says I should just draw a picture because, man, my pictures were pretty mean or badass last year, I thought, although my class groaned and told me they weren't as good as I thought. So what happens is we've got 2 types of overlap that we can consider. We can talk about head-on, which is taking these hybridized orbitals, sp2 or sp3s, and bonding them head-to-head. So notice that here the electron density is between the atoms. And then we can take the leftover p orbitals, meaning unhybridized, and overlap them in what's called a pi bond. Where notice here that the electron density is above and below the atom. Meaning my overlap is right here and my overlap is right here, so that's where the electron density is. Notice how when we draw these bonds we show some electron density above the atom and kind of below it because we have to bend the bonds, right? It's not a 100% perfectly good picture of what the atom looks like, but it's approaching it. So what happens then when we take a look at that is, and this is one of those things where I almost think this is like a balloon diagram. I feel like I should hire some guy to put balloons together like this. Because, you know, be like, dude, can you make me a formaldehyde molecule? So what this is this is literally a picture. Oh, this is not the right picture, but this will work. So this is a picture of this molecule right here. Carbon double bonded to a carbon with the hydrogens. And so note that here's my trigonal planar molecule. Notice I've got 3 lobes. Here's one of them that's the single bond between carbon and carbon. and then I've got the single bonds between carbon and hydrogen. And notice that the pi bond is formed from the overlap of these orbitals. Now, notice this just draws a big tube between them, right? Realize that if I drew the molecules really close together, what it's saying is that I've got one big p orbital like this, and the second one's big p orbital overlaps it like that. So literally the p orbitals overlap. That's forming that pi bond. And so what we see is that this carbon-carbon double bond has one sigma overlap, and it has one pi overlap. And what that allows us to do is very neatly to explain many of the features of carbon-carbon or carbon-oxygen double bonds, which is that one bond is very non-reactive. That's the sigma bond, because the electrons are in the middle. And one bond in that is very reactive. That's that pi bond, and that's because those electrons are exposed. Now, I have to be honest, to really truly look at this picture, if you look in your book, it's got a better picture in that it shows the process as a series of steps, something that I can't quite form or draw very well. And so I think your book actually has better pictures than even these, and maybe I should go steal the pictures from your books. Because now that I look at it, these pictures are definitely not from your book. Because or at least they're not showing the whole picture. They're just blow-ups of some of them. So what we're learning is that, okay, we'll just put it here in the corner. If I have sp3 hybridization, that means I have a tetrahedral shape. If I talk about sp2 hybridization, that gives me that trigonal planar shape, which means that I have 3 sigmas plus 1 pi that I can form for bonds. So the nice thing about all this orbital mixing and this complicated math is it's predicting everything we need to know. So it's good that if you have these pictures in your head, but also if you just remember that when you see something as sp3 that we know that's, or I'm sorry, when you see something that's tetrahedral, which is pretty easy to figure out, especially if you're building the Lewis structures in class or on a test or in the lab, then you can figure out what sort of hybridization must have occurred for it to happen. Okay, so let's look at the next one. This is called sp hybridization. And note that it's an s and a p, so that gives me 2 hybrid orbitals. And then there's 2 p orbitals that are left over that are unhybridized. And so notice here's my 2 sp hybrid orbitals. They still have that sort of uneven shape. And notice that when I overlap the lobes, it gives me sort of that linear thing. And so notice that here's, one capable of making a sigma. Here's another sigma. I've got a pi here, and it's a little hard to see, but that faint kind of greenish in the background is my other set of p orbitals. So those are my 2 p orbitals. And then I've got, 2 sp orbitals. And so what that starts to predict is things that are linear in nature, or things that have triple bonds. Now, you thought that last balloon picture was tough? Check out this balloon picture, okay? So if you take a look at it, notice that it is labeled, that, here's an s orbital, or here's a sp orbital, here's an sp orbital, here's one p orbital, and then there's another p orbital. And so actually, let's do this with color. Not that you guys are writing or taking notes, but if you ever watch the lecture, notice that, for instance, the red, even though it's in 2 places, that represents 1 p orbital. And notice that if I color in, say, in purple, this p set of orbitals, that represents 1 p orbital. So the p orbitals are strange in that they have 2 lobes, but it really is only the location of 1 electron. And then if I take a look at it, that's 1 sp orbital that's hybridized. And this would be, say, the other sp orbital that's hybridized. So there really is 4 orbitals there. And so then notice that what happens for a triple bond is, and it's really tough to see, this isn't very, the colors aren't as good here as they are in your book. I really do recommend looking in your book. But, you know, I've got one sigma bond, and then notice that I've got one pi bond that's above and below it, and then the other pi bond is coming in and out of it. So what that really is trying to show is this picture right here. And it's really saying that one of the bonds is sigma, and that there's two pi bonds, meaning there's two of those overlaps above and below it. And that matches really well because the sigma bond is unreactive, and the two pi bonds are super reactive. Maybe super is too much, but it's very reactive. And that's exactly what we see in experiments too. That molecule is called acetylene. Have you guys heard of acetylene gas? Yeah, acetylene. That's the common name. What do we use acetylene for? Welding, right? Because it's super reactive. You mix it with oxygen, you burn it, it produces a lot of heat. And so we use acetylene gas. Now, you've also heard of methane, right? That's what we normally call natural gas. So compare the energy content of a natural gas burning versus acetylene burning. Which one's better for welding? Yeah, acetylene. I mean, natural gas is what we use in our Bunsen burners. Have we welded anything with our Bunsen burner lately? No. But can we weld things with acetylene? Certainly. Okay, so this is getting to the rest of them. So to invoke the last two, we have to remember that those violated the octet rule. And so for their hybridizations, we get something weird like, for instance, sp3d2. Actually, is that the one I want to do? No, we want to do s3pd1 because that's the one we're on. So notice that that's 5 orbitals. Therefore, we expect to make 5 bonds. And if you take a look at this picture, notice these 3 are in one plane. And then we've got the 2 on the top and bottom. That just looks like our trigonal bipyramid, right? And so the idea is that I want you to realize that you're already used to the shapes. You just have to be able to count up to 5, right? See, 1s, 3 p's, and 1d. What is that? That's, oops, 5. Okay, I showed both hands, so that technically is 10, but just one hand is 5. And then if we take a look at the last one that violates it, we call the hybridization for this sp3d2. Well, that leads to our octahedral shape, where, you know, we've got these 4 forming that square, and then we've got one up above it that's kind of forming that lovely octahedron, and then I've got one below it that forms the other part of that octahedron. Does that look like an octahedron to you? It does if you use your imagination. And I got to be honest, you know, if we pull out the models, it's 10 times easier to see. So realize that all 5 of the shapes predicted by Lewis structures that we've been talking about also are predicted by valence bond theory and this hybridization of orbitals. Plus, we get a better explanation for carbon-carbon double bonds and a better explanation for carbon-carbon triple bonds. And so valence bond theory neatly explains a ton of stuff. And since it explains that ton of stuff, you know, we just have to go with it and say, hey, we like this theory. Here's 2 sets of double bonds. I don't know if we care about that. And then this is starting to get into molecular orbital theory, so we'll cruise past that. We need some more blank slides to start molecular orbital theory. So let's talk about molecular orbital, or MO theory. I'm so lazy most days, especially on a Friday, that it even pains me to have to write molecular orbital theory out once, much less a bunch of times. So what we want to look at for molecular orbital theory is, again, what are the flaws in valence bond theory? Why did we have to move to a new theory? So let's start with the 2 flaws in valence bond theory that we want to explain. The first one is that it incorrectly predicts whether things are paramagnetic or diamagnetic. Paramagnetic or diamagnetic. And magnetism is something very easy to figure out, meaning that if something is paramagnetic, it's attracted to a magnetic field, and if it's diamagnetic, it's not attracted to a field. And maybe I should write that down. Except and see, this is where Jay really kind of is annoyed with this. Yes, so diamagnetic means it's not magnetic. And paramagnetic means it's magnetic. And probably the single biggest example of that, and I think your book has a lovely picture in it, is figure 7.15. And what it shows is one field of a magnet here, one field of a magnet here, and a cloud of liquid oxygen suspended in the field. So a very easy experiment to do, very obviously visually that oxygen is magnetic. But see, to be not magnetic, you have to have all electrons paired. And to be paramagnetic, that means that you have unpaired electrons. And since you have unpaired electrons, you can interact with a magnetic field. And so if I take a look at oxygen, and I draw its Lewis structure, all the electrons are paired. Which means, oops, according to theory, this should be non-magnetic. But in experiments, it's very obviously magnetic. And so the idea is that we've got huge visual evidence, just something that's so trivial to show that people knew about it for a long time and simply said, well, we need to tweak valence bond theory to do that. Well, turns out it's a little harder to tweak it than that. And then the other kind of flaw in valence bond theory is that the electrons are in individual atomic orbitals, and therefore aren't really shared. Meaning that our simple idea of that overlap equals sharing is flawed. That simply overlapping two orbitals doesn't mean the electron is stuck right between them, because most of those orbitals have an area in those orbitals where the electrons aren't stuck between them. And so what we have to do is we have to move from atomic orbitals to the concept of molecular orbitals. And so the very first kind of precept of molecular orbital theory is simply realizing that atomic orbitals belong to individual atoms, and they can be thought of as either like the s, p, and d orbitals, or as the hybrid versions like sp3, sp2, etc. But that they belong to individual atoms. Whereas MO theory says that what we really have is not atomic orbitals, that's what I just got done talking about, molecular orbitals. And that these are a combination of atomic orbitals, but they span an entire molecule. So instead of belonging to one or the other atom, they belong to both atoms. And maybe the easiest way to see this is to kind of draw a picture. And the idea is that this, again, works on that idea of mathematically mixing waves. Except the result and how we do it is different. So if I take a 1s orbital from one atom plus an s orbital from a second atom. So see, hybridization for the other hybrid orbitals was orbitals on the same atom, right? Now I'm talking about orbitals from two different atoms that we're mixing together. And so that mathematically results in a different thing. And what happens is it predicts something weird. predicts that there's two types of orbitals. There's where we mix them together and we get an orbital that looks kind of like this, that's symmetrical around both nuclei. And then it predicts a set of orbitals that look like this, where the electron is really only around one of the atoms, or it's around the other. And there's what we call, well, maybe I should do that in the middle. There's what we call a node. So there's a node with no electron density between the atoms. Whereas here, the orbital and the two electrons that would be in it are equally shared between both atoms. And there's a picture in your handouts that's supposed to be showing that. I'm not going to bother going back to it. Really, my picture is pretty awesome, I think, so I think we can not worry about it. Just double checking something. Oh, I know, I'm going the wrong way in my pictures. I just want to make sure that there's not something else I should show in that picture. But I'm pretty happy with it. Yeah, oh, I should point out that I guess we can point out that this is called a additive combination. And we can think about that as the two waves are constructive interference. And then we have what's called subtractive combination. And that's where the two waves interfere destructively. So when you're mixing waves, they can basically be either in phase with each other or out of phase with each other. It's kind of like saying if I take this wave and it's identical wave and I add them together, I get a wave that's twice as big, right? So that's kind of for the additive. And if I take a wave like this and I take its opposite and I add them together, I really get a flat line, right? If I have two waves that exactly cancel each other out. So that's kind of what's going on here. When we mix waves from two different atoms, they can either interfere constructively, be shared equally among both atoms, or they can interfere destructively and end up being sort of between both atoms. We have names for these. This is called a bonding orbital because the electrons really are shared, and we call that a BO. And we have what are called non-bonding orbitals, meaning that if electrons are in those orbitals, they're not being shared between the atoms. They're not helping the atoms to stick together. We're going to call those NBOs because non-bonding orbital and bonding orbital is way too much for Jay to write. He's a lazy SOB, and instead we'll go ahead with the bonding orbital and non-bonding orbital notation. So what that means for a simple molecule, like for instance if I take a look at hydrogen, it means that I'm saying that I've got a 1s orbital on one hydrogen, and I've got a 1s orbital on my second hydrogen, and I'm making them mix. And so what I'm really doing is I'm making two new sets of orbitals. And one set of orbitals is higher in energy, and one set of orbitals is lower in energy. This is my bonding orbital. Notice that it's lower in energy, and this is my non-bonding orbital. Notice that it's high in energy. And what we tend to call this is a sigma orbital, sigma 1s, and this is going to be my sigma 1s star, where the star means that it's a non-bonding orbital. So what this is saying is that this is an atomic orbital. This is another atomic orbital. But if I mix them together, I don't know what awesome color I'm going to come up with. Let's see. We get our molecular orbital. Oops. Spell it right. What the hell? This is our molecular orbital. And what that allows us to do then is to build up a series of things. Like for instance, if I take a look at helium, and helium, it again has just 1s orbitals. And if I mix them together, I get something like this. And I mix them together and I get something like that. Here's my sigma orbital, here's my sigma star. This is my bonding orbital. This is my non-bonding orbital because it's higher in energy. Now, how many electrons does helium have? Oops, helium. Element number 2. So the idea is this helium has 2 electrons, this one has 2 electrons. And maybe I should go back. I did kind of forget this. Hydrogen, of course, has 1 electron and 1 electron, right? And then when I put the electrons in the molecular orbitals, both electrons are in a bonding orbital, right? It means it's bonded together. Oops, backwards, I need to go forwards. Here, if I put my electrons in, I guess we'll go back to red, notice that I've got 4 electrons in my molecular orbital. So 4 electrons in a molecular orbital, 2 in a bonding orbital, 2 in a non-bonding orbital. The net effect is no bond. So does the molecule He2 exist? No. Does the molecule H2 exist? Yeah. And so molecular orbital theory can predict why we would get hydrogen making a molecule, whereas we would not predict it for helium. It also predicts nice things like, for instance, hydrogen, since it's got paired electrons, should be diamagnetic, right? Meaning it shouldn't be attracted to magnetic fields. And if you do take hydrogen and try to interact it with a magnetic field, then you get nothing. I'm going to do one last little picture, and then we'll call it quits, and we'll finish up the tail end of this on Monday, and we'll also pick up, well, I got to be honest, I am not sure if we should do Chapter 8 next. A certain part of me says let's skip Chapter 8 and skip Chapter 9 and go straight to Chapter 10, where we start using, or we keep using all these molecular, or those Lewis structures, so there's no chance that you'll forget them. But then I'm afraid that I might have to bring in a bunch of stuff from previous chapters. And I got to be honest, this is where a little bit where I dislike your book, because there's 3 directions we can kind of go, and your book doesn't clearly differentiate which direction you're going, and so you get stuff from all 3 chapters mixed up together, and it's a little confusing sometimes. Not that this isn't, but you know, this is at least in one chapter where it belongs. So we can also form molecular orbitals from p orbitals. And so we have to recognize that there's going to be 2 sets of p orbitals. There's going to be the set that form head-on. That's going to lead to a sigma bond. And there's the set of p orbitals where, remember, that overlap is up above and up below. That's going to lead to what we call pi orbitals. And I'm not going to try to draw these. Your book has much more beautiful pictures than me, so we'll just scroll up and kind of go take a look at them. So notice this was our picture where we took a 1s from one atom and a 1s from another. Now what I'm saying is I'm going to take a, for instance, a 2p orbital in the x direction and a 2p orbital in the x direction. I'm going to put them together, and here I'm taking a 2p y orbital, say, and a 2p y orbital, and I'm putting them together. Notice that this is head-to-head. This is more like it's above and below. So this is our pi, this is our sigma. Notice that it gives us, again, a high energy non-bonding orbital and a low energy bonding orbital. And then it gives us, again, a high energy NBO and a low energy bonding orbital. Notice that that looks almost like what we predicted from valence bond theory, doesn't it? With where you got a hot dog on top and a hot dog on bottom. I always think they look like hot dogs personally. Does that make sense? Yes, no, no, yes? I don't know. What it does is it allows us to realize that we can make 2 pi bonds, because I've got the p orbitals that are aligned this way, and I've got the p orbitals that are aligned this way, and then that last set of p orbitals is making the head-to-head. So I get 2 pi's and a sigma, and what that really does is it starts giving me this complex diagram, where if you take a look at it, you can see that here's the molecular orbitals made for mixing two s orbitals. Here's the molecular orbitals for mixing the two p orbitals. We get a bunch of pi bonding, sigma, sigma, or pi and sigma, and it gets a little bit more complicated after that. But I'm well over, well, I don't know if I'm well over my time limit, but I definitely am over my time limit, so just not sure if it's worth, let's just finish it off. Screw this. It'll be easier to just finish it off and be done with it. So we're making our molecular orbitals, and we can start putting some atoms in it. And I guess really what we want to do is we want to take a look at oxygen. So let's just skip to O2. How many electrons does oxygen have? Total. Oh, look, a periodic table. Oxygen is element 8. So that means that there's 8 electrons from that oxygen and 8 electrons from that. Now notice what your picture doesn't show is it doesn't show the 1s's. And the reason it doesn't bother with the 1s's is because we know they're full. So the idea is that I've got 1, 2, 3, 4, 5, 6. Notice I'm filling them from lowest to highest and then pairing up, right? So what, I was at 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What do you notice about those electrons? They're unpaired in different p orbitals. Therefore, that means that it's paramagnetic. And that really, when we draw our oxygen atom, we should realize that I've got 1 sigma overlap here. Oh, I'm sorry, I've got these cancel out. Notice the nice thing about it is if the orbitals are full, the non-bonding and bonding cancel out. So here's my NBO and my BO and my NBO. Those cancel. And so I'm left with a set of pi orbitals and a set of sigma orbitals. So here's my sigma bond, here's my pi bond. And what it's really saying is that we should draw oxygen like this. And that really 2 of the electrons are also paired up. And so we really should draw it with some unpaired electrons in our picture. And so the nice thing about molecular orbital theory is it explains the magnetic properties. The shitty thing about molecular orbital theory is it leads to fucking ugly pictures like this that we hopefully want to not see again. Now, I don't know, I kind of rushed the ending. What we're probably going to do is we'll say, give me a new slide. Slide. So what we're going to say is, for next week, on Monday, we'll finish up / review MO theory. Tuesday, homework. This is chapter 7. This one was homework 7E is due. That's on valence bond theory. Wednesday, we'll have homework 7D due. That's on molecular orbital theory. And we'll also finish the lab on Lewis structures. And then for the big question mark that Jay gets to decide this year is whether we're going to do chapter 8, 9, or 10 next. I don't know. I got to be honest, to me, it makes no difference. What I'm really going to try to do is I really want to just do chapter 10 next. But the problem would be is that if chapter 10 has too much stuff